Time is the most familiar force in your life, yet it might be the universe's greatest trick. We feel it passing, we plan by it, we watch it slip away. But when physicists peer into the deepest laws of reality, they find something shocking. The fundamental equations describing our universe often contain no time at all. They are static and eternal, a frozen landscape where nothing flows. This creates a profound mystery. If time is not a basic ingredient of the cosmos, then why does it feel so real? How does the relentless river of our experience emerge from a timeless foundation? By the end of this journey, you will understand one of the most radical ideas in modern physics, the concept that time itself is not fundamental but emergent. We will explore how this single shift in perspective rewrites the story of the universe, from the smooth certainty of Isaac Newton to the quantum foam at the edge of a black hole. What would it mean if the past, present, and future are not what they seem? For centuries, this intuitive feeling of time found its perfect expression in the work of one man. Isaac Newton gave time its first true scientific definition, and in doing so, he built the bedrock of classical physics. He envisioned time as an absolute and universal backdrop. Picture a vast, invisible river flowing at a constant, unchanging rate throughout the entire cosmos. Every event, from the fall of an apple to the orbit of a planet, was simply a passenger on this river. This absolute time was independent of everything. It did not care about matter or motion. It simply was a cosmic clock that ticked the same way for everyone, everywhere, whether you were standing still on Earth or racing among the stars. This model was staggeringly successful. It explained the heavens with unprecedented precision and gave engineers the tools to build our modern world. More importantly, it cemented our deepest intuition into a law of nature. Time was fundamental. It was the stage upon which the drama of the universe played out. This Newtonian view is so powerful that it still dominates our daily lives. When you check your watch, schedule a meeting, or feel a deadline approaching, you are living in Newton's world. You are trusting in that absolute, flowing river. But what if that river is an illusion? What if the stage itself is part of the play? That absolute river of time flowed unchallenged for over 2 centuries. Then a young patent clerk in Switzerland asked a simple, dangerous question. What would happen if the speed of light were absolute? Albert Einstein followed this question into the heart of physics and emerged with a revelation that shattered Newton's perfect stage. His theory of special relativity declared that time is not universal, it is personal. The rate at which time flows depends entirely on how fast you are moving. This is time dilation. Imagine 2 identical, incredibly precise clocks. One stays on Earth, the other is placed on a spacecraft moving at a significant fraction of light speed. When the spacecraft returns, the 2 clocks will disagree. The clock that journeyed will have ticked slower, less time will have passed for it. This is not a mechanical error. It is a fundamental feature of reality. For the moving clock, time literally stretched. Einstein then wove this insight into his general theory of relativity, where gravity, the force that shapes the cosmos, is not a pull but a warp in the fabric of spacetime itself. A massive object like the sun creates a dimple in this fabric, and just as a ball would roll into that dimple, planets follow the curved paths we call orbits. In this view, time is woven together with the 3 dimensions of space into a single, 4-dimensional fabric. This is spacetime. The flow of time you experience is your unique path through this fabric. Crucially, this also shatters the idea of a universal now. 2 events that appear simultaneous to one observer may happen at different times for another moving observer. There is no single, privileged present moment for the entire universe. Einstein's work was a monumental leap. It dethroned absolute time and revealed a dynamic, interwoven cosmos. Yet, for all its revolution, spacetime in relativity remains a fundamental, continuous entity. It is the new stage, a dynamic, bendable, interwoven stage, but a stage all the same. The fabric is assumed to exist. The question of where this fabric came from, or whether it might itself be woven from something more basic, remained untouched. The stage was set, but its origin was still a mystery. Yet Einstein's fabric of spacetime, for all its malleability, was still a smooth and deterministic stage. When physicists ventured into the realm of the very small, they discovered a reality where the stage itself dissolves into a ghostly, probabilistic haze. Quantum mechanics governs the behavior of particles and forces at the smallest scales, and its core mathematical description possesses a startling property. The fundamental equation, the Schrödinger equation, is largely time-symmetric. This means the mathematics does not inherently distinguish between past and future in the way our everyday experience does. The equations work just as well if time were to run backwards. They describe possibilities and probabilities, not a single, flowing narrative. This creates a profound disconnect. In our macroscopic world, you can break an egg, but you never see the pieces spontaneously reassemble into a whole. This arrow of time, pointing firmly from past to future, seems absent from the quantum rulebook. The disconnect becomes even more extreme when we apply quantum principles to the entire cosmos. In the 1960s, physicists John Wheeler and Wheeler-DeWitt attempted to combine general relativity with quantum mechanics to describe the universe as a whole. Their resulting equation, the Wheeler-DeWitt equation, presented a universe frozen in an eternal instant. The variable for time simply vanished from the mathematics altogether. It described a static quantum state of the entire cosmos, a single, timeless snapshot. This is the famous problem of time in quantum cosmology. If the most fundamental description of reality contains no time, then where does our powerful, inescapable experience of it come from? It suggests that time, as we know it, is not a feature of the universe's deepest layer. Instead, it must be something that emerges, like temperature emerging from the frantic motion of countless molecules. The quantum description might be fundamentally atemporal, a realm of pure potential and connection, from which the flowing river of time condenses into existence. This leaves physics with two magnificent yet seemingly incompatible descriptions of reality. On cosmic scales, Einstein's general relativity paints a picture of a dynamic, curving spacetime, a grand stage where gravity directs the motion of the stars. On the microscopic scale, quantum mechanics reveals a ghostly world of probability and connection, a realm where the very idea of a smooth, continuous stage begins to break down. Each theory is spectacularly successful in its own domain, but the universe does not have separate rules for the large and the small. It is one reality. So what happens when these two titans meet? Where does the smooth fabric of spacetime interact with the fuzzy uncertainty of the quantum? The answer is that our current understanding shatters. This is the unfinished quest for a theory of quantum gravity, a single framework that can describe the force that shapes galaxies using the rules that govern particles. We need this theory to understand the most extreme environments in existence, to peer into the very first moments after the Big Bang, when the entire cosmos was smaller than an atom, a domain where quantum effects and gravity were inseparably entwined. To comprehend the baffling singularity at the heart of a black hole, where spacetime curvature becomes infinite. In these arenas, our two great theories point in opposite directions, and the central casualty of their conflict is time itself. General relativity needs a spacetime fabric to bend. Quantum mechanics, at its most fundamental, suggests that fabric might be an illusion. To build a bridge between them, we cannot simply stitch the two pictures together. We must be willing to dismantle our most basic assumptions. The quest for quantum gravity is not just a technical puzzle. It is a philosophical mandate that forces us to ask, what are the true, fundamental ingredients of the universe? And if time is not one of them, then what in the world are we actually feeling? The universe's deepest laws might be timeless, but your experience is anything but. This stark contradiction points toward a radical solution, a concept that reshapes how we define reality itself. It is called emergence. An emergent property is something real, something you can measure and experience, that arises from the collective behavior of simpler parts. It is not a fundamental ingredient, but a consequence of their interaction. Think of temperature. To a single molecule, the idea of hot or cold is meaningless. A molecule just has kinetic energy, it jiggles, but take trillions upon trillions of those jiggling molecules, and a new macroscopic property emerges: temperature. The warmth of a cup of coffee is a real, tangible phenomenon, but it is not a fundamental force of nature. It is a story told by countless tiny actors. Or consider the fluidity of water. A single water molecule is not wet. It cannot flow or form a wave, yet bring a vast ensemble of these molecules together, and through their interactions the property of wetness emerges. The smooth, continuous flow of a river is a collective illusion, a higher-level description that makes sense of an underlying chaos. This is the paradigm shift. Our most familiar experiences might be like the wetness of water, not like the molecules themselves. They are real in their consequences, but derivative in their origin. And this brings us to the ultimate emergent candidate, time itself. Could the relentless flow you feel, the distinction between past and future, be a similar kind of collective illusion? Perhaps time is not woven into the universe's foundation, but condenses from it like mist rising from a timeless sea of quantum connections. If so, then finding time is not about discovering a new particle or force. It is about learning to read the cosmic story being told by the universe's most basic and possibly timeless components. The most undeniable feature of time is that it points in one direction. You remember the past, you anticipate the future, and you cannot reverse the sequence. This is the arrow of time. Its origin, surprisingly, is not found in the fundamental laws of physics, but in a principle that governs disorder. It is called the second law of thermodynamics, and it states a simple, profound truth. In any closed system, the total amount of disorder, or entropy, always increases or stays the same. It never spontaneously decreases. Think of a drop of ink in a glass of water. At first, the ink is concentrated, a region of high order, then it begins to diffuse. The molecules spread out, mixing chaotically with the water molecules until the entire glass is a uniform, pale color. This is an increase in entropy. The system has moved from a state of low disorder to high disorder, and crucially, you will never see that process spontaneously reverse. The pale mixture will not suddenly gather itself back into a single, dense drop of ink. This irreversibility is the arrow of time in its most tangible form. But here is the mystery. The individual laws governing the collisions of each water molecule and ink molecule are perfectly time-symmetric. If you could magically reverse the velocity of every single molecule, the ink would indeed recoalesce into a drop. The microscopic rules do not forbid it. So why does it never happen in our reality? The answer lies in statistics and the sheer number of particles involved. There is only one way for the ink to be a neat drop, a state of very low entropy. But there are an astronomically vast number of ways for the ink to be spread out and mixed. When the system evolves, it is overwhelmingly more likely to stumble into one of the countless disordered states than to accidentally find its way back to the single, perfectly ordered one. The arrow of time emerges from probability. It is not a fundamental force pushing the universe toward disorder. It is a story told by unimaginable numbers. Our experience of a directed, irreversible flow of time is a consequence of the universe starting in a state of exceptionally low entropy, like that single drop of ink in the vast glass of reality. Everything that has happened since, from the formation of galaxies to the brewing of your morning coffee, is part of the statistical drift toward higher entropy. This gives us our first concrete example of an emergent aspect of time. The directionality we feel so deeply is not written into the bedrock laws. It is a collective phenomenon, a ghost in the machine of countless particles. If the arrow of time can emerge from complexity, what other features of time might be illusions of scale? But if time's arrow emerges from statistics, what about time's very tick? Its basic flow from moment to moment. To find an answer, we must step into a world where even the notion of a single, objective reality becomes fluid. This is the domain of Carlo Rovelli's relational quantum mechanics, a framework that proposes a radical reimagining of time itself. In this view, time is not a universal backdrop, not even a bendable fabric. It is a story that only exists in the telling. Rovelli's starting point is a core, puzzling feature of quantum mechanics. Properties of a particle, like its position or momentum, are not defined in absolute terms. They only become definite relative to something else through an interaction. An electron does not have a specific location until it is measured by another system. There is no grand, God's-eye view of reality with everything in a definite state. Instead, the universe is a vast web of correlated events, a network of interactions where information is exchanged. From this web, time emerges. Think of it like a cosmic game of telephone. System A interacts with System B, and in that interaction, each system records a change in the other. This record becomes a tick of a clock, a marker of before and after for those two systems. But System C, off in another part of the network, might have a completely different sequence of interactions. There is no single master timeline synchronizing everything. Time is the partial order we infer by looking at the network and ignoring the dizzying quantum details. We see a sequence, a story of cause and effect, but only from our limited perspective within the network. In this picture, asking what time it is for the universe as a whole is a meaningless question. Time is not a container the universe sits inside. It is a language that subsystems use to describe their relationships to each other. The flow you feel is the story of your own continuous interactions with the world around you, a narrative woven from countless quantum exchanges. Your now is not the universe's now. It is yours alone, generated by your place in the relational web. This relational web gives us a structure, but it does not yet explain the persistent sensation of flow. For that, Carlo Rovelli offers a more specific and startling idea, the thermal time hypothesis. It suggests that the very tick of time is not a fundamental rhythm of the cosmos, but a thermal effect, a kind of heat. In this view, what we perceive as the passage of time is actually the universe's natural tendency to evolve from a state of lower entropy toward higher entropy. Remember, entropy is a measure of disorder or the number of possible microscopic arrangements a system can have. Our universe began in a state of remarkably low entropy, an extraordinarily special and ordered configuration. The thermal time hypothesis proposes that this special state is not just the reason for time's arrow, but for time's very existence, because we, as complex systems within the universe, are fundamentally ignorant of its exact, full microscopic state. We perceive this statistical drift as a flow. Time emerges from our lack of knowledge. It is the story our brains tell to make sense of the universe's inevitable slide into a more probable, more disordered state. To grasp this, think of a simple, closed system like that sealed box of gas. If you could know the position and velocity of every single molecule, the entire history and future of the box would be determined by the timeless laws of motion. From that God's eye view, there is no flowing time, just a static set of relationships between all particle positions at all possible configurations. But you are not a god, you are a macroscopic observer. You cannot possibly track trillions of molecules. Your only access to the system is through coarse, averaged properties like temperature and pressure. From your limited, ignorant perspective, the gas appears to evolve. It mixes, it reaches equilibrium, it never unmixes. That appearance of evolution, of something happening, is what you call the passage of time. The thermal time hypothesis scales this idea up to the entire cosmos. Our universe has a particular, low entropy starting point. We, as complex subsystems within it, are perpetually out of sync with its full microscopic detail. Our inevitable interaction with it, our constant measurement of it through our senses and instruments, forces us to describe it using averages and probabilities. And that description necessarily includes a variable we call time. The flow is not in the fundamental equations. It is in the interaction between our partial perspective and the universe's hidden complexity. In this radical picture, time is the temperature of the universe. It is a real, measurable effect, but one that exists only because of our relationship to a deeper, timeless reality. But if time is a story born from our ignorance, what is the universe like from a perspective that sees everything? Some physicists argue we must be willing to abandon the idea of succession entirely. This is the path taken by the theoretical physicist Julian Barbour, who proposes a vision of reality so radical it makes the flowing river of time vanish completely. He calls his timeless landscape Platonia. Imagine for a moment every possible configuration of the entire universe, every single arrangement of every particle, every star, every galaxy, and every thought. Each of these is a complete frozen snapshot, a perfect and eternal now. In Barbour's view, this is all that exists. There is no past that fades away, no future waiting to be born. There is only an infinite, static landscape of these nows. Our entire cosmos, from the Big Bang to the distant future, is not a movie playing out on a screen of time. It is more like a vast cosmic library where every single frame of that movie exists simultaneously on its own shelf. There is no film strip connecting them, no projector moving from one to the next. So where does our powerful, undeniable feeling of movement and change come from? Barbour suggests that within this infinite library, certain nows bear a special relationship to each other. They contain structures that are similar. One now might show you reading this sentence. Another now, placed near it on the shelf, shows you having just finished the previous sentence. These nows are not connected by a flow of time, but they are arranged in a sequence of similarity. Our conscious experience, then, is like a light hopping from one now to a very similar now, and then to another. Each jump creates the illusion of continuity, of one moment leading to the next. The sensation of time passing is the sensation of this sequence of static states. In this picture, there is no fundamental clock ticking underneath it all. There is only the landscape and the path our awareness takes through it. You do not move through time. Time is the measure of the difference between one eternal state and the next. This idea turns our intuition inside out. The past is not gone. It is simply another region of Platonia, eternally present. The future is not unwritten. It is already there, fully formed. Our journey is not through time, but through a timeless garden of possibilities, and our consciousness is the walker that gives the garden the appearance of a path. Yet this timeless library of nows presents us with a profound and intimate mystery. All these theories, from the thermal flow to the static landscape, must confront a single, stubborn fact of your existence, the vivid, undeniable experience of the present moment. This is the problem of the now. Physics, in its quest for objective truth, has systematically dismantled the idea of a universal present. Einstein's relativity shattered it, showing that my now and your now, if we are moving relative to each other, are not the same. There is no privileged slice of spacetime that everyone agrees is the present. Quantum gravity and timeless theories go even further, suggesting the present moment may not be fundamental at all, just a useful story. And yet, here you are not reading this sentence in the past or the future, you are reading it now. This feeling is the very center of your conscious experience, a bright, moving point of awareness that seems to travel from one moment to the next. How can something so central to being alive be so absent from our deepest descriptions of reality? This gap is not a small oversight. It is a chasm between the objective, third-person world of physics and the subjective, first-person world of experience. Emergent theories of time are not just trying to explain clocks and entropy. They are attempting to build a bridge across this chasm. They must account for how a universe described by timeless equations or a landscape of frozen states gives rise to this luminous flowing now. Perhaps the answer lies not in the fabric of space-time, but in the fabric of something else, the complex information processing systems that perceive it. The moving present may not be a feature of the external world, but a feature of how a brain or any sufficiently complex system organizes information. It could be the way consciousness makes sense of a reality that is, at its root, a vast network of correlated events. The present moment feels real because you are real, and your process of experiencing is real. But its movement, its flow, might be the ultimate emergent phenomenon, a story written by a conscious observer trapped in the beautiful, statistical drift of a timeless cosmos. This search for time in the structure of reality leads us to a surprising place, the strange and wonderful world of quantum entanglement. This is the phenomenon Einstein famously called spooky action at a distance, where two particles become so deeply linked that measuring the state of one instantly determines the state of the other, no matter how far apart they are. In our quest, entanglement is not just a curiosity. It is increasingly seen as the potential thread from which the fabric of spacetime itself is woven. And to understand how, we can look to an unexpected branch of science, condensed matter physics, which studies the collective behavior of vast numbers of particles in materials. Here, physicists regularly encounter emergent phenomena, where entirely new properties arise that are not present in the individual parts. A classic example is superconductivity. A single electron cannot be a superconductor, but when you cool certain materials to extremely low temperatures and arrange billions of electrons in just the right way, they move in perfect, frictionless unison. The property of zero electrical resistance emerges from the collective dance. This is the paradigm we can apply to time. Could time be like the superconductivity of the universe, an emergent property of a deeper, timeless quantum network? Some of the most promising models for quantum gravity suggest exactly that. They propose that space itself is not continuous but emerges from a vast web of interconnected quantum units, often visualized as a network of nodes and links, like an unimaginably complex cosmic spiderweb. In this web, the nodes might represent tiny volumes of space, and the links between them represent quantum entanglement. Now, here is the crucial insight from condensed matter physics. In certain complex quantum materials, physicists have shown that an extra dimension can effectively emerge from the entanglement patterns between the particles. You start with a system that exists in, say, 2 dimensions, but the way its parts are quantumly connected makes it behave as if it has a third. This is not science fiction. It is a mathematical reality in the lab. Apply this thinking to the cosmic web. If space emerges from the network of entangled nodes, could time emerge from the dynamics of that entanglement? The theory suggests that what we perceive as the flow of time could be a story told by the changing patterns of connection within this timeless web. A change in the entanglement structure between 2 regions of the network might be what we record as one tick of a clock. The sequential ordering of events, the before and after we hold so dear, could simply be the most logical way to describe how these quantum correlations evolve. In this picture, the universe is not in time. Time is in the universe, a narrative generated by its internal quantum relationships. It offers a breathtakingly concrete possibility. The river of time you feel might be the current flowing through an ocean of endless, silent connection. The idea of time as a story woven from quantum connection finds a powerful voice in one of the most ambitious theories of reality. Loop quantum gravity takes the radical step of applying quantum principles directly to the fabric of spacetime itself. It does not assume that space and time are smooth and continuous. Instead, it proposes they are woven from tiny, indivisible threads. The theory's foundation is a spin network, a web of intersecting lines where each line carries a quantum of area and each intersection a quantum of volume. Picture the universe not as a smooth sheet, but as an unimaginably fine mesh with the tiniest possible weave. This is space in its raw quantum form, a buzzing network of discrete grains. In this picture, there is no background stage. The network itself is everything, but a static network cannot give us change or history. For that, the network must evolve. The theory imagines a realm of all possible spatial configurations, a kind of cosmic landscape called superspace. As the spin network changes from one configuration to another, it does not move through time. It simply transitions to a different, adjacent state in this timeless landscape. If you could stack every possible transition, like flipping through the pages of a cosmic flipbook, you would not see a smooth movie. You would see a frothing, churning structure known as a spin foam. Each bubble and connection in this foam represents a quantum event, a fundamental transition in the geometry of space. This is where our classical reality begins to condense. The smooth, continuous spacetime of Einstein's relativity, the stage we take for granted, is not fundamental here. It is an average, a large-scale picture that emerges when you zoom out from the frenetic quantum foam, just as the smooth surface of a pond emerges from the chaotic dance of countless water molecules. In this framework, time as we know it does not drive the changes. It is the other way around. Time is the story we tell about the sequence of these quantum transitions. The relentless tick of a clock is our macroscopic experience of the universe's geometry hopping from one quantum state to the next. The flow is not in the equations, but in the unfolding narrative of the spin foam's evolution. Loop quantum gravity offers a breathtakingly concrete vision, a universe where time is not a river but the current, emerging from a timeless sea of quantum geometry. The quantum foam of loop quantum gravity reveals a universe stitched from discrete threads, but another theory proposes an even more radical kind of emergence. It suggests that our entire four-dimensional reality, time and all, could be a hologram. This is not science fiction, but a serious principle born from the fiery paradoxes of black holes. The holographic principle emerged from a stunning discovery about these cosmic enigmas. Physicists found that the maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. Think of that for a moment. All the information about every star, planet, or particle that ever fell into a black hole is not smeared inside its three-dimensional volume. It is painted like a cosmic fresco on its two-dimensional boundary. The three-dimensional interior is a projection of that data. This was the first hint that our intuitive sense of dimensions might be an illusion. String theory then extended this idea far beyond black holes. It proposed that our entire universe might operate on the same principle. The three spatial dimensions you move through, plus the dimension of time you experience, could be a holographic projection from a two-dimensional surface at the cosmic horizon. In this view, we are not living inside the universe. We are living on a lower dimensional screen, and our rich, four-dimensional reality is a decoded image, much like a three-dimensional hologram emerges from the flat, etched patterns on a piece of glass. The profound implication is that spacetime itself, the very arena of existence, is not fundamental. It is emergent. It is a collective, approximate description that arises from the quantum interactions of countless bits of information living on a distant, lower-dimensional surface. And if spacetime is emergent, then time, which is woven into it, is doubly so. The flow you feel would be a necessary part of the projection, a feature that only makes sense in the decoded image, not on the timeless code surface where the true, fundamental laws reside. This turns our understanding inside out. The universe is not a container with stuff in it. It is a relationship, a dynamic translation between a simpler, perhaps timeless, quantum system and the rich sensory world we perceive. Your entire history, every memory and future hope could be written on the surface of a sphere you will never see. The hologram theory paints a breathtaking picture, but it still starts with a surface, a screen, a fundamental arena. What if we strip away even that? What if the most basic ingredients of reality are not dimensions or fields, but something far simpler, events and their relationships? This is the stark, elegant vision of causal set theory. It begins with two profound assumptions. First, spacetime is not continuous. It is made of discrete, indivisible grains like the pixels on a screen, but far more fundamental. Second, and more radically, the most basic property these grains possess is not a location in space or a moment in time. It is causality, the ability for one event to influence another. Imagine the universe as a vast cosmic ledger, but instead of recording financial transactions, this ledger records only one thing: causal relationships. Each entry is an elementary event, a fundamental grain of happening. The only notation in the ledger is a simple arrow, pointing from one event to another if the first can be said to have caused or influenced the second. One grain causes two others, which each cause three more, and so on, building up an immense branching network of pure causality. This is a causal set, a universe described not by coordinates or distances, but solely by an order of before and after. In this raw mathematical structure, there is no space as we know it. There is no smooth flowing time. There is only this web of cause and effect, a tapestry woven from the threads of influence itself. So how do we get from this sparse network of arrows to the rich, four-dimensional world we inhabit? The answer lies in a process we have seen before: emergence through approximation. The smooth, continuous spacetime of Einstein's theory, with its elegant curvature and definite intervals, is not the fundamental reality in this view. It is a large-scale, approximate picture that emerges when you look at the causal set from very far away. Think of a bustling city seen from an airplane window. From that height, you see smooth roads, flowing rivers, and orderly neighborhoods. You do not see the individual cars, the people on the sidewalks, or the cracks in the pavement. The city's continuous appearance is an illusion of scale. In the same way, the four-dimensional continuum of spacetime is what we see when we blur our vision and look at the causal set's immense complexity. The dimension of time, in particular, emerges from the cumulative order of the network. The relentless sequence you experience, the march from past to future, is the story told by following a chain of causation through the set. Your now is not a universal slice, but your particular location within this ever-growing web of events, and your past is the set of all grains from which you can trace a causal arrow to your present grain. In causal set theory, time is not a river. It is the current that flows along the paths of possible influence, a direction carved out by the fundamental architecture of causality itself. The timeless web of causal relationships brings us back to the most stark mathematical expression of this mystery. The Wheeler-DeWitt equation stands as a monument to the problem of time. When physicists John Wheeler and Bryce DeWitt applied the rules of quantum mechanics to the entire cosmos, Their resulting equation described a universe frozen in a single, eternal instant. The variable for time simply did not appear. This is the frozen formalism, a description of reality where nothing ever happens, where the universe is a static quantum state, a single frame in a movie that never plays. It is a profound and unsettling result. If this is the most fundamental description, then the bustling, evolving cosmos we see around us, from spinning galaxies to growing trees, is somehow an illusion. The equation seems to tell us the universe just is, not that it becomes. For decades, this was viewed as a catastrophic flaw, a sign that the theory was wrong or incomplete. But what if we have been reading it incorrectly? What if the problem is not with the equation, but with our assumption that time must be an external, master clock ticking outside the universe? The frozen formalism forces a radical shift. If there is no external time, then time must be something inside the universe. It must be an internal property, a relationship between parts of the whole. To recover the flow of time, physicists search for an internal clock, a physical variable within the universe that can play the role of time for everything else. Imagine you are in a windowless, perfectly sealed room. There is no external day or night to mark the hours, but you notice a single candle burning steadily on a table. You cannot see time pass, but you can measure the decreasing height of the wax. The candle becomes your clock. Its changing state orders your experience. This is the quest within the Wheeler-DeWitt universe. The equation may not contain time, but it contains many variables that change relative to each other. One candidate for the cosmic candle is the volume of space itself. As the universe expands, its total volume increases. This expansion could provide a natural, internal tick. One moment is defined by the universe having a certain volume, the next moment by a slightly larger one. The flow of time would then be inextricably linked to the expansion of space. Another possibility is a background field, like the Higgs field that gives particles mass, oscillating in a regular way throughout the cosmos. Its cycles could serve as the pendulum for reality. In this view, time is not a stage. It is a story told by one part of the universe to all the others. The ticking is not fundamental, it is emergent, a rhythm generated by the universe's own internal dynamics. The frozen formalism is not a picture of a dead cosmos. It is a picture of all of time at once, and our journey through it is simply us, as a subsystem within that whole, using one part of the scenery to navigate the eternal landscape. This idea of an internal clock transforms the frozen formalism from a paradox into a profound insight. Within the timeless quantum state described by the Wheeler-DeWitt equation, nothing changes from an external, God's eye view. Yet from inside the system, change is all we see. The solution is to realize that the universe contains its own timekeepers. One part of the cosmos, something that changes slowly and predictably, can serve as a reference for everything else. Imagine two pendulums swinging in a sealed, windowless room. You cannot see the clock on the wall outside, but you can watch one pendulum. Its steady, rhythmic swing allows you to measure the motion of the second pendulum. You can say the second pendulum completes 3 cycles for every 1 cycle of the first. Time in that room is not an external force. It is the story of correlation, of how one part of the system moves relative to another. Now scale this idea to the entire cosmos. In the early universe, a prime candidate for this master pendulum is the geometry of space itself, its curvature or its volume. As the universe expands from an incredibly dense state, its overall shape evolves in a smooth, monotonic way. This slow, grand change in geometry becomes the internal clock against which every other process is measured. The rapid dance of quantum fields, the formation of the first particles, the birth of stars, all these events are not happening in an external time. They are happening with the geometry. Their evolution is correlated with it. When we say a star formed 5 billion years after the Big Bang, what we are really saying is that the event of star formation occurred when the universe's volume had expanded to a certain specific size relative to its starting point. The geometry provides the tick, and everything else provides the talk. Time emerges from this vast network of internal correlations. It is not a river flowing past the universe. It is the current of relationship flowing within it, a rhythm generated by one part of the cosmos for the benefit of all the others. Your heartbeat, the orbit of Earth, the decay of a radioactive atom, these are all smaller, nested clocks within the grand clock of cosmic expansion, each telling a story of correlation with the whole. But this grand internal clock of cosmic expansion leads us back to the very beginning of its tick, to the most profound mystery of all. The Big Bang is often described as the moment the universe began, a fiery explosion from a single point. Yet this picture, for all its power, contains a hidden assumption. It assumes the Big Bang was an event that happened in time, at a specific moment on a cosmic timeline. But if time itself is emergent, then this story must be rewritten. Perhaps the Big Bang was not the first event in time, it was the first event of time. It was the moment time itself crystallized from a timeless state. This shift in perspective transforms our deepest cosmological questions. In a universe with emergent time, the classic query, what came before the Big Bang, might be as meaningless as asking what is north of the North Pole. Before implies a prior moment in time, but if time did not exist, there is no before in the usual sense. There is only a timeless quantum gravitational realm, a state of pure potential described by the frothing spin foam or the dense web of a causal set. In this realm, the concepts of cause and effect as we know them may not apply. There is sequence without succession, possibility without actuality. The Big Bang, then, marks the transition from this timeless quantum fog into a universe where a clear direction of time, a thermodynamic arrow, emerges and takes hold. It is the point at which the internal clock of the universe started its first, irreversible tick. This is not a moment of creation from nothing in a philosophical sense, but a phase transition in the very nature of reality, like water freezing into ice. The timeless quantum geometry froze into a classical, expanding spacetime, and with that freezing, the river of time began to flow. What we call the initial singularity is not a point of infinite density in space and time, but the boundary where our classical concepts of space and time simply cease to be meaningful. It is the shore of a timeless ocean, so asking what happened before is like asking what lies beyond the edge of a map. The map does not extend that far. Our language, built on sequence and causality, struggles to describe a state where those things do not yet exist. The origin of time is not a point in history we can point to. It is the horizon of history itself. These ideas are breathtaking, but they face a monumental challenge. How do you test a theory that suggests our most basic experience is an illusion? When the target of your experiment is time itself, traditional laboratory methods seem to fall short. Yet, science does not advance on philosophy alone. It demands evidence, and physicists are devising remarkably clever ways to search for the fingerprints of an emergent reality. The quest begins by asking what signatures a grainy, quantum spacetime would leave on the universe we can actually measure. If spacetime is a smooth continuum, as Einstein described, then a photon of light, traveling for billions of years from a distant quasar, should make a perfectly straight and unwavering journey. But if spacetime is a quantum foam at the tiniest scales, a churning sea of virtual particles and fluctuating geometry, then that long journey might not be so smooth. The photon would effectively be bouncing over an invisible, bumpy terrain. These minuscule bumps could cause subtle differences in the travel time of photons with different energies. A high-energy gamma-ray photon might feel the foam's texture differently than a lower-energy optical photon, causing them to arrive at our telescopes slightly out of sync after a multi-billion-year voyage. This is not science fiction. Observatories like the Fermi Gamma Ray Space Telescope and the MAGIC atmospheric telescopes actively analyze light from the most violent cosmic explosions, searching for these telltale delays. Finding such a signature would be like discovering that the universe has a pixel size, a fundamental graininess to its very fabric, offering our first direct hint that smooth spacetime is indeed an emergent approximation. Another avenue searches for cracks in the symmetry of the cosmos. Einstein's special relativity is built on a principle called Lorentz invariance, which states that the laws of physics are the same for all observers, no matter their constant velocity. This symmetry is what makes spacetime a unified, seamless fabric. But if that fabric is woven from discrete quantum threads, that perfect symmetry might break down at extremely high energies or small scales. It would be like looking at a beautifully woven tapestry from a distance. It appears smooth and uniform, but if you bring a powerful magnifying glass right up to the threads, you might see the individual knots and the tiny spaces between them, revealing a structure that is not perfectly smooth or symmetrical at the microscopic level. Physicists design exquisitely sensitive experiments to look for these potential violations. They might study the behavior of ultra-precise atomic clocks in different orientations, or search for subtle changes in the properties of particles accelerated to incredible energies in machines like the Large Hadron Collider. Any verified deviation from Lorentz invariance would be a seismic event in physics, a strong indicator that we are seeing glimpses of the discrete, underlying structure from which spacetime and time themselves emerge. These experimental paths are indirect and immensely challenging. They are not about seeing a quantum of time in a microscope. They are about detecting the faintest of whispers in data, whispers that suggest the smooth, continuous stage of our reality has a hidden, grainy scaffolding underneath. Each null result, every time we find that spacetime appears perfectly smooth, helps constrain the theories, telling us what the universe is not, and a single, verified positive signal would change everything. It would move the question of emergent time from the realm of beautiful speculation into the domain of observable science, offering our first tangible clues that the river we are floating on is not fundamental, but the magnificent collective motion of something far deeper and more strange. The search for time's origin forces us to confront a question that is as much about philosophy as it is about physics. If time emerges from a timeless foundation, does that make our experience of it any less real? This is the heart of a profound debate, one that hinges on the meaning of a single, loaded word, illusion. To call something an illusion suggests it is a false perception, a trick of the mind that does not correspond to anything in the external world. A mirage in the desert is an illusion. There is no water, only refracted light. So, if physicists tell us the fundamental equations are timeless, does that relegate the entire drama of history, memory, and anticipation to the status of a cosmic mirage? Many thinkers argue this is the wrong way to frame the discovery. They propose a more nuanced and powerful idea, that time is not an illusion but a real emergent phenomenon. The distinction is everything. Think of a whirlpool in a river. From the perspective of the individual water molecules, there is no whirlpool. There are only molecules obeying the laws of motion and colliding with one another. The whirlpool has no independent existence at that fundamental level, yet from our macroscopic viewpoint, the whirlpool is undeniably real. It has structure, it has predictable behavior, it can exert force on a stick you put in it. It is a robust, higher-level reality that emerges from the collective dance of the parts. To call the whirlpool an illusion because it is not a fundamental ingredient of water would be to miss the point entirely. It is a real pattern with real consequences that exists at a different scale of description. Time, in this view, is the universe's grandest whirlpool. The feeling of a moving present, the unidirectional arrow from past to future, the very ticking of clocks, these are not false perceptions. They are the authentic, tangible patterns that arise when a timeless quantum system reaches a certain scale and complexity. They are as real as the warmth of a fire or the wetness of water, real in their consequences and in their inescapable grip on our lives. This shifts the philosophical stakes dramatically. We are not being told our lives are a lie. We are being offered a deeper understanding of what makes our lived reality possible. The debate then naturally flows into the deepest waters of human experience, consciousness, and free will. If the moving now is a feature of complex systems processing information, does that mean consciousness creates time, or does time enable consciousness? The answer may be that they co-emerge, two facets of the same complex, relational process within the universe. As for free will, the idea of a deterministic, timeless block universe can feel stifling, as if every choice was already etched into the cosmic ledger. But if the future is not yet real in the emergent, relational sense, if it is still being woven by the ongoing network of causal events, then genuine possibility and openness remain. Your choices are part of that weaving. The meaning of change itself is transformed. In a timeless foundation, nothing changes. In our emergent reality, change is the most fundamental truth we know. It is the story of the universe exploring its own possibilities, and we are the characters and the narrators within that grand, unfolding tale. Yet for all its explanatory power, the emergent time paradigm is not without its fierce critics. The most visceral challenge is this: if time is not fundamental, how do we ever recover the one thing we know best, the vivid, undeniable sensation of the present moment? Physics has brilliantly explained the relativity of simultaneity, showing that my now and your now can differ. But in doing so, it has seemingly abandoned any hope of a universal present. Emergent theories often go further, suggesting the present is not a feature of the world at all, but a feature of our perception. To many, this feels like a profound failure, a retreat from explaining reality into explaining it away. If the now is just a cognitive construct, a story the brain tells, then what is the story about? Critics argue that a complete theory of reality must ultimately account for the raw data of conscious experience, not dismiss it as an irrelevant side effect. The charge is that by making time emergent, physics risks becoming disconnected from the very phenomenon it set out to describe. A second, deeply technical criticism strikes at the logical heart of the idea. If the fundamental laws are completely symmetric with no built-in arrow, how does a robust, universal arrow of time ever emerge in one direction and one direction only? We saw that thermodynamics gives us the arrow from statistical probability, starting from a low entropy past. But where did that incredibly special, low entropy initial condition come from? Saying the universe began that way simply pushes the mystery back a step. Some proposals suggest quantum gravitational effects in the very early universe might naturally lead to such a state, but no consensus has been reached. The criticism is that deriving a consistent, one-way arrow from perfectly reversible foundations remains an enormous and possibly insurmountable hurdle. Without a compelling origin story for the initial low entropy state, the emergent arrow of time can feel like a description, not an explanation. Perhaps the most sweeping criticism is philosophical. If we take timelessness seriously, our entire language of change, cause, and becoming seems to lose its footing. We speak naturally of events happening, of processes unfolding, of the future being open. But if the fundamental description is a static block or a network of correlations, then in what sense does anything actually happen? The charge is that eliminating time makes physics descriptively rich but dynamically sterile. It gives us a map of reality but seems to silence the narrative. How can a theory that has no place for genuine change ever be considered a complete picture of our world, a world defined by change. Critics from this camp argue that rather than trying to eliminate time from our foundations, we should be seeking new, more fundamental laws that inherently incorporate its flowing, dynamic nature. They see the move to timelessness not as progress, but as a surrender to a mathematical convenience that ignores the central drama of existence. This tension is not a small academic dispute. It is a fundamental rift over what the ultimate goal of physics should be: to provide a detached God's-eye view of the whole, or to ground the reality of the world as we actually live and experience it. But this fierce debate over emergence is not the final word. For every physicist who sees time as a magnificent illusion, another argues it is the bedrock of reality itself. This competing view holds that time is not a story that emerges, but a fundamental character in the cosmic script from the very first line. In this camp, the smooth, continuous flow of time is not an approximation to be explained away, but a direct reflection of a deeper, intrinsic property of the universe. Some approaches to quantum gravity are built on this very foundation. Take the theory of causal dynamical triangulations. Unlike its purely causal cousin, this framework takes time seriously from the start. It constructs spacetime from tiny, fundamental building blocks, but it imposes a crucial condition: a clear, discrete ordering that distinguishes past from future at the microscopic level. In this model, the universe is assembled from four-dimensional geometric shapes, but they are glued together in such a way that a global time direction is preserved at every step. The arrow of time is not an afterthought, it is baked into the recipe. The resulting universe looks remarkably like our own, with the familiar three dimensions of space and one of time emerging naturally from the dance of these tiny pieces. Here, time is not a collective fever dream of timeless atoms. It is the conductor of the orchestra, an essential ingredient that guides the formation of reality itself. Similarly, within the vast landscape of string theory, many formulations treat time as a fundamental dimension right alongside the dimensions of space. The strings that make up all matter and energy vibrate not just in space, but within a spacetime that is assumed to exist. In these views, asking where time comes from might be like asking where the canvas comes from in a painting. It is simply part of the framework necessary for the picture to exist at all. The core of this fundamentalist perspective is a philosophical stance, a belief that our direct, powerful experience of temporal flow is a clue, not a confabulation. It suggests that physics should seek to explain this experience, not explain it away. The sensation of a moving present, the aching reality of memory and anticipation, these are not glitches in a timeless matrix. They are signals from the deepest layer of existence, telling us that becoming is as real as being. This debate is very much alive, a vibrant and unresolved tension at the heart of theoretical physics. It is not a conflict with a clear right and wrong, but a conversation about where to place the foundations of our reality. Do we build from the timeless and derive the temporal, trusting that our lived experience will condense from the equations? Or do we start with time and change as givens and build a universe that inherently contains the drama we know so well? The answer will not come from philosophy alone, but from the slow, meticulous work of matching theory to the faint whispers of experimental data. Until then, the question remains open, a testament to the profound mystery of the one thing we all share and yet understand the least. If time is not a river we float upon but the current itself, then the entire landscape of our history and destiny is transformed. This perspective forces us to re-examine three of our most enduring puzzles: the nature of the future, the reality of the past, and the tantalizing dream of time travel. In a universe where time emerges from a timeless web, are our lives a script already written or a story being composed in real time? First, consider the future. The classic block universe of relativity suggests a single, four-dimensional loaf of bread, where every slice from the Big Bang to the distant end exists eternally. This can feel deeply deterministic, as if every choice you will ever make is already a fixed part of the cosmic geometry. But an emergent time framework offers a different, more dynamic vision. If the future is not yet part of the emergent classical reality, if it is still a froth of quantum possibilities in the timeless substrate, then it may be genuinely open. Your decisions are not reading lines from a pre-written script. They are acts of writing, helping to determine which of the countless possible configurations in the timeless landscape will become the next now in the emergent sequence. The future is not a destination waiting for us. It is a process of becoming, a continuous crystallization of one possibility out of many. This does not grant magical freedom, as we are still bound by physical law and prior cause, but it reintroduces a profound sense of potential. The universe is not playing a recording, it is composing a symphony, and we are both the musicians and the notes. Now turn your gaze backward. Does the past still exist? In our daily experience, the past feels gone, a memory fading into nothingness. Yet physics, particularly relativity, treats the past as a real region of space-time, just as real as the space behind you. If time is emergent, this reality takes on a fascinating character. The past is not erased. It is the set of events that have already become correlated into the stable, classical record of the universe. It is the part of the timeless network that has been measured and fixed by the relentless increase in entropy. Think of it like a path being paved through a meadow as you walk. The ground behind you is still there, marked by your footsteps, but you are no longer standing on it. The past exists, but not in the same way the present does. It exists as information, as correlation, etched into the fabric of reality. Your memories, the light from distant stars, the geological layers of Earth, these are all echoes of that fixed record. The past is not a ghost, it is the foundation upon which the present moment is being built. This brings us to the grandest puzzle of all, time travel. The idea of visiting the past or the future is a staple of fiction, but in an emergent framework, it faces even steeper conceptual cliffs. If the past is a fixed record of correlations, a stable pattern in the universal network, what would it mean to travel back to it? You would not be entering a living, breathing moment. You would be attempting to insert your contemporary, complexly correlated self into a snapshot that has already been taken. This would create a logical paradox, a violent mismatch in the web of cause and effect. More fundamentally, if time is not a dimension you move through but a story generated by change, then traveling along it is not like taking a train to another city. It would be like trying to step into a different chapter of a book and expecting to rewrite the plot while the ink is already dry. The universe's internal consistency, the very correlations that generate time's arrow, seems to forbid such violations. The future presents a different challenge. If the future is not yet real in the classical, emergent sense, there is simply nothing to travel to, no definite slice of space-time to arrive within. You will be trying to journey to a place that has not yet been paved. This does not make the cosmos feel smaller. Instead, it reveals that our deepest questions about time were framed by an incomplete picture. We asked about moving through time as if it were a tunnel. But if time is the tunnel's walls emerging as you walk, then the very question of traveling through it changes into something else entirely. A question about rewriting the story of reality itself. Our entire experience of time is filtered through a biological processor of staggering complexity, the human brain. While physics debates whether time is fundamental or emergent, neuroscience reveals a more intimate truth. Our minds are actively constructing the sensation of time in every waking moment. You do not perceive time directly, you assemble it. Your brain takes a chaotic stream of sensory data, a blur of light, sound, and touch, and weaves it into a coherent narrative with a past, present, and future. This construction project happens in a window psychologists call the specious present, a brief span of about 2 to 3 seconds where our brain blends immediate perception with recent memory to create the feeling of now. Think of listening to a melody. You do not hear a series of isolated, frozen notes. You hear a tune because your brain holds the just played notes in a temporary buffer and seamlessly stitches them to the one you are hearing right now. That seamless stitch is your present moment. It is not a knife edge between past and future, but a short, integrated story. This psychological present is what gives continuity to your reality, turning a flickering series of neural signals into the smooth flow of conscious experience. But how does this constructed present develop an arrow? Why does it feel like it is moving forward? The psychological arrow of time appears to be a cognitive projection, a story your brain tells based on cause and effect and the irreversible process of memory formation. When you drop a glass and see it shatter, your brain registers the sequence cause then effect and files the cause as a memory before the effect is fully processed. This ordering, built into the very architecture of learning, creates an inescapable directionality to your mental timeline. Your brain constantly takes the present, packages it into memories, and uses those memories to predict the immediate future. This predictive loop, this constant forecasting of what comes next based on what just happened, may be the engine of our subjective time flow. It is a cognitive arrow that generally aligns with the universe's thermodynamic arrow because our brains evolved within that same stream of increasing entropy. Yet it is distinct, a layer of emergence all its own. A brain injury or certain neurological conditions can disrupt this delicate machinery, causing time to feel slowed, sped up, or even lost altogether, revealing that our most personal sense of time is a fragile and magnificent construction. This suggests that the river of time you feel is not one current but many, a thermodynamic flow, a relational network, and a psychological story, all converging to create the single, powerful reality of your lived experience. These diverse threads of thought do not unravel the fabric of reality, but instead weave it into a richer, more intricate tapestry. The thermodynamic arrow, the relational web, the holographic projection, and the causal network are not competing truths. They are different languages, each describing the same breathtaking possibility from a unique vantage point. They converge on a single, radical insight that the time we live in is a coarse-grained, approximate, yet undeniably powerful description that emerges from a more fundamental, timeless reality. Think of it like observing a bustling city from a satellite, from a street-level map, and from the live feeds of traffic cameras. Each view is valid, each reveals a different layer of truth, but none captures the full, living complexity of the metropolis itself. The thermodynamic view explains the irresistible direction of time's flow, the current that carries everything from order toward disorder. The relational and quantum views describe the raw material from which this current is made, a network of interactions and entanglements where sequences are born. The holographic and causal frameworks suggest the very stage of space and time is itself a projection, a higher-level story told by a simpler, lower-dimensional code. These are not contradictions, they are complementary perspectives on a single, staggering process of emergence. Your experience of a flowing present is the thermodynamic and psychological story. The quantum correlations between particles provide the relational substrate, and the large-scale, smooth spacetime you move through is the classical hologram that condenses from it all. This synthesis offers a profound resolution to the problem of time. It is not that time is an illusion in the sense of being false. It is that time, as a continuous, flowing river, is a robust and real phenomenon that exists at a certain level of description, much like the wetness of water or the melody of a song. It is what the universe looks like when you step back from the frenetic, timeless buzzing of its most fundamental components and observe the grand, statistical patterns that result. The past, present, and future we navigate are not written into the bedrock of being. They are the magnificent and inevitable narrative that unfolds when a timeless cosmos of pure potential begins to explore its own possibilities, and in doing so tells itself a story. Yet this grand synthesis, for all its explanatory power, is not the end of the story. It is a map with vast, uncharted territories. Three profound questions stand at the frontier, their answers still hidden in the quantum fog. First, what is the precise microscopic mechanism? We speak of time emerging like wetness from water, but we do not yet have the mathematical equivalent of understanding exactly how individual molecular attractions create a cohesive, flowing liquid. We need a detailed recipe, a step-by-step account of how specific quantum interactions, the entanglements, the causal links, the spin network transitions coalesce into the smooth, directed river we experience. Which quantum events count as a tick, and how do trillions of them synchronize to create a universal rhythm? The blueprint is still being drafted. Second, can we find a single, unified mathematical framework that derives all aspects of time? Right now, we have compelling but separate sketches: thermodynamic arrows, relational networks, holographic projections. They point in the same direction, but they are not yet one picture. The ultimate theory must weave these threads together, showing how the direction, the flow, and the very dimensionality of time are all different faces of the same emergent phenomenon. It must tell us why these features always appear together in the universe we inhabit. Finally, and perhaps most crucially, how does the quantum to classical transition lock in the emergent flow? The fundamental quantum realm is a place of superposition and probability where multiple possibilities coexist. Our classical world of definite events and a single timeline feels solid and irreversible. The crossing point between these two realms, the moment potential becomes actual, seems to be where time truly crystallizes. But how does the act of measurement or interaction somehow stitch together a consistent history from the quantum haze, creating the unchangeable past? Understanding this crossing is the key to understanding why time feels so concrete and one-way, emerging from a foundation that is neither. These are not small puzzles. They are the deep currents running beneath our entire explanatory map. Answering them will require more than elegant philosophy. It will demand a new mathematics, one capable of describing how timelessness gives birth to history and how possibility hardens into the unshakable now. Until then, the mystery remains beautifully, tantalizingly open. The most radical shift is not a new particle, but a new way of seeing. The emergent time hypothesis asks us to trade a familiar picture for a deeper, more elegant one. We are not moving through a container called time. Time is a consequence of the universe's own internal relationships. The cosmos is not a thing evolving in time. It is a timeless structure from which the story of time crystallizes, like a melody emerging from the silent connections between notes. Your life is not a journey along a pre-existing river. You are part of the current itself, a participant in the weaving of the narrative. This transforms the universe from a clockwork mechanism into a dynamic, self-telling story. The mystery of existence shifts from asking what happens next to asking how the beautiful illusion of next is conjured at all. This quest is far from over. Laboratories and observatories around the world are hunting for the subtle signatures of a timeless foundation, while theorists work to stitch the many threads of this idea into a single, coherent tapestry. The question of what time truly is remains one of the greatest open frontiers in human thought, so we turn it to you. Does this vision of an emergent, flowing now resonate with your own experience of reality? Or does it feel like a step too far into the abstract? The conversation between our lived reality and the fundamental nature of the cosmos continues, and your perspective is a vital part of that grand, ongoing discovery.